Okay, so the next section, moving along, we're going to talk about what are called conditional propositions and logical equivalence. So last time on Wednesday, we were talking about logical connectives, ways of putting propositions together. And the ones that we talked about last time were the and statement, which we called a conjunction, the or proposition, which we called a disjunction, and then the third one was called the negation, which corresponds to the word not. And today we're going to look at a new kind of way to put together propositions called the conditional proposition. And also another one, we'll get there. So let's dive right in with an example. This one. This sentence is an example of a conditional. If you make an A on all of your exams, then you will pass discrete math. And the structure here is an if-then statement. And that's what we mean by a conditional. Okay, so moving on to the definition, I'll just write it out clearly. If you have two propositions, P and Q, so P and Q are letters standing in for something like my propositions here, which were in English, then the proposition if P then Q is called a conditional proposition, like I said. And just like the and the or and the negation, this kind of proposition also has its own notation. We'll start with P and then draw an arrow pointing to the right at Q. So whenever you see these symbols, this means in English, if P, then Q. And there's a few more words that you'll see come up when we're talking about conditional propositions. The first proposition, P, is sometimes called the hypothesis. And the proposition Q, the second one, is often called the conclusion. So returning to the example, you would call, you make an A on all of your exams, the hypothesis, and you will pass discrete math, the conclusion. So that kind of matches up with how we think of hypotheses and conclusions. This should be an I for singular. So when is the conditional proposition true? That's the next thing we need to talk about. And we'll just look at the same example. So P is going to be, you make an A on all of your exams. Q is going to be, you'll pass discrete math. And we're still looking at if P, then Q. So let's think about what happens if P is true. So if you make an A on all of your exams, when is the conditional statement true? So what I mean is, what has to happen with Q if P is true? So what happens if P is true? You make an A on all of your exams and you pass discrete math. Is my conditional statement true?
Yes.
Good. Yeah, so if P is true, if you do make that A on all of your exams, then you definitely have to pass discrete math in order for this statement to be true. The conclusion Q must be true if you do pass, or if you do make an A on your exams. Okay, so that's pretty clear, I think. What happens if P is false? So if you don't make an A on all of your exams, what can we say about the conclusion? You will pass discrete math.
We could say it doesn't have to be true.
It doesn't have to be true, right? So you could fail. Maybe you really bombed your exams. Could you pass? If you don't make an A on all of your exams, could you still pass?
Possibly.
Right, maybe you didn't make A's, but maybe you actually did make B's or C's. So either way, this conditional statement would still be true. Do you have to put not P if that's the case? No. We don't have to change the original. So the idea here is that if P is false, then this conclusion could be true or false, so you could pass or fail, but your overall statement to begin with is still true. Because nothing happened that contradicted your original statement. It just doesn't matter. If you don't make an A on all of your exams, then what you said originally, it's not actually guaranteeing anything happens. You could pass or fail. So that second part, the part where P is false, where you don't make an A, this, I think, is the more confusing part the first time you see it, because it leads to this truth table, which I'll put on the next page. Okay, so we're making a truth table for the conditional proposition that we've been looking at. We'll have to fill in the left column with the possible values for the simple statements P and Q, simple propositions, like we did last time. So there's 4 possible combinations of truth values. And we know if P is true, so if you did make an A on all of your exams, then you definitely do have to pass. And that's true on this column. And if you made an A on all of your exams, but somehow you ended up failing, well, that just doesn't work. This is false. It makes your statement false. But as we discussed, if you don't make an A on all of your exams, maybe you made a B on one of them, then you could still pass or fail, and that wouldn't contradict what you were saying. So this conditional statement is true, even if or is true all the time, even if you fail. Or I say fail. You wouldn't necessarily have to fail an exam. You could make a B. Okay, any questions before we do a more complicated example? Okay, so I want to look at a more complicated kind of truth table. So you're going to have to do truth tables like this with more complex kinds of statements or propositions on your homework. So I wanted to be sure to include an example. And this one has three simple propositions. And as we saw last time, that means we're going to have 8 rows, 8 different possible combinations of trues and falses. And I'll fill it in the same way I did last time. Start with 3 trues, and then have 1 false statement, 1 false proposition. And that can happen 3 ways. And then you're going to have 2 false propositions, or 3 false propositions. And now we'll need to fill in the next column. So if you just read your textbook, often what they do is they'll just put the whole complex compound proposition here and then a single column of truth values. But I find when I'm doing this that it's much easier if instead of writing the whole thing, I actually make several columns over here. So what I can do is I can add a column for each of the component pieces of this more complicated proposition. So instead of writing the whole thing, maybe I'll do a column for P or Q, just this first part. And then I can make another column for not R, the negation of R. And then once I figured out the truth values for these 2 pieces of the bigger compound proposition, I'll make a last column for the overall thing. So P or Q, then not R. So for these columns, we just have to think back to last time. P or Q, the disjunction, is true as long as at least one of these 2 statements is true. So here we have 2 trues again. There's 1 true, but that's still true, the or statement. And again, we have 2 trues. And then this should be a true. I had a little bit of a typo. So we still have 1 true. And we still have 1 true. And then in these last 2 rows, we finally have P and Q both false. So this is the first time we get a false down here. Okay, so Davian, what I'm doing, just to go back, I broke down this kind of complicated looking proposition into 2 pieces. And I'm finding the truth value of my 2 pieces. So for P or Q, in order for this to be true, I need one of these 2 statements to be true, or at least one. So I'm looking at the truth values for P and the truth values for Q to fill in this column. Okay, and then when I look at this column for the negation of R, so now we're looking at the right-hand piece of my conditional statement, I look at the truth value just of the simple statement R, and the negation switches it. So if I have a true, this becomes a false, and then just do it for the rest of them. So false becomes a true, true becomes a false, true becomes a false, false becomes a true, false becomes another true, and then false, true to finish off.
On that second to last one, why do we say it's false even though P and Q are both false?
On this row here?
Yeah, since the and isn't there, since they're false. How am I trying to say this?
So you're looking at this
and not.
Are you looking at this one here?
Yeah. Well, no.
Or this
I'm
one?
looking at the original.
Over here.
False, false, true. Yes.
Okay.
So my question is, since P and Q are false, and the statement is P and Q not R, why is R false? Since that is, since that's already false, why is R also
okay.
false?
So when I'm filling in this column, I'm only looking at R. So you can kind of just completely ignore these.
Okay.
And you can totally ignore this one too.
All right.
So this is all we're looking at right now. Does that make more sense? Okay. Okay, so now that I have the truth values for my two simpler, well, we start with the simplest, and then we get a little bit more complex, and then we put everything together. Now I'm going to look at the overall statement. And we have to think back to the table for the conditional. And we can see the only time the conditional statement is false, if P then Q, is if we have a true on the left as our hypothesis, but our conclusion is false. And everywhere else we get true statements. So I'll keep that in mind down here. So now we're going to ignore all of this stuff because this is the left-hand side of my conditional. This is the hypothesis. And this column is the conclusion. So now we can totally ignore this stuff on the left and just look at these truth values. So if I get a true here and a false there, that's the only time that this is going to be false. Yeah, and Davian, you're right on the first row. So what about the second row? True and true. It's true, good. And then we have a true and false again, and we actually have that twice. So we have two more falses. And then we have true, 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 true. And remember back up here, when both the hypothesis and the conclusion are true, the conditional is true. So both of these rows are true. And then in the bottom, we have falses for the hypothesis on the left side. And in the original truth table, we saw that if the hypothesis is false, then the conclusion doesn't really matter. It's just always going to be true. So both of these rows will have trues. Okay. So that's it. That's how you finish it off. Are there any questions over this example, or any more questions? Okay. So this technique of trying to break down your complicated proposition into pieces, I think will come in handy on the homework for this section and also the one that we did last time. So give this a try if you get stuck on something complicated. Okay, so something I'm going to point out before we move on is when I've been talking about this conditional statement, I've always used an if-then sentence structure. But in English, when we're just using words, there's several other ways that we can say conditional statements, like this one. And in this example, I want to cook, but I'm lazy. I don't want to do any dishes. And here's my proposition. I will cook pasta for dinner only if there's a clean pot, because I don't want to clean anything. So which of these two things is my hypothesis? Which is the conclusion? Okay, so William is saying this is backwards. So should this be, if there's a clean pot, then I will cook dinner?
Yes.
Or should it be, if I cook pasta, then there's a clean pot? Okay, so everyone is wrong, and that's why I wanted to make sure I point this out. Oops. Not if I cook clean pasta. If I cook pasta for dinner, then there's a clean pot, is the correct way to think about this. So it's actually written in the correct order already. So the reason why goes back to the truth table. So if I cook pasta for, or I will cook pasta for dinner only if there's a clean pot. If I don't cook pasta for dinner, then, well, there could be a clean pot or not. And my statement is true. So does that make sense? I feel like I need to explain that more, but I don't know how.
So with the only if, there's still a possibility of it not happening, even if the if is true.
Right. So I will definitely only cook pasta if there's a clean pot, but I might still decide not to cook pasta. That's the subtext here. So this is different than the opposite way. If there is a clean pot, then I'll cook pasta for dinner. That's something different. Because this way around, if there's a clean pot, then I have to cook pasta. And that's not what I mean by this statement. Okay, so there are a few other ways to write conditional statements, like I said, and there are quite a few examples in your textbook. So I encourage you to glance through those examples when you're doing your homework. Yeah, William, maybe I might cook pasta if there's a clean pot, but if there's not a clean pot, I definitely won't. Okay, so let's look at, we shouldn't combine English and math. Yeah, so the reason is that when we're talking or writing, usually we're a little bit wishy-washy in what we're saying. Whereas in math and logic, we have to be precise. And this is exactly what you have to do when you're programming a computer. You have to be really precise in what you mean, because if you're wishy-washy, the computer might think you mean something else than what you actually meant. Okay, so the next idea, so here's a new definition, is the reverse order of the conditional. So I still have two propositions, P and Q. Then this proposition, if Q, then P, is called the converse of the other way around, if P, then Q. And just so it's clear, let me write here, the order is switched. And an example of this, and hopefully this illustrates why they're not the same thing. An example of a normal conditional statement could be, if it's raining, then it must be cloudy. Right, there must be a cloud dropping rain. The converse is different though. So this is your conditional. Proposition. And it's putting the conclusion first, right? So if I reverse the order, if it's cloudy, then it's raining. This would be the converse. So I picked this example just to illustrate that these are actually very different kinds of propositions. Because the first one, I think we can all agree, has to be true. If there's raining, then there actually has to be a cloud that's dropping rain on you. But if it's cloudy, it doesn't have to be raining. It could just be cloudy. So keep in mind that when you switch the order, the meaning of your proposition changes. Maybe I'll put a note here. Different meaning. Okay, so the converse was kind of just a variation on the regular old conditional proposition. The next one is actually something new. How they're different is the confusing part. Yeah, that's why I picked a concrete example. So they definitely are different, even though they look so similar. When you write down the symbols, at least. Up here. Okay, so this new definition is going to be for the proposition P if and only if Q. And this is called a biconditional proposition. And we'll get to the reason eventually why it's called a biconditional. So the other one is just called conditional, and the word bi means two. So I'm somehow making this two conditional. And the biconditional statement, P if and only if Q is true. And let me fill this in, sorry. So the notation for the biconditional proposition is this. So instead of an arrow pointing to the right, now you have an arrow pointing to the left and the right. And this proposition is true when P and Q have the same truth value. Oh, so you're close. They don't have to both be true. They just have to have the same truth value. So they could both be false. So let me fill in the truth table so that you can see. Right, if both sides are false, if P and Q are both false, then they both have the same truth value. So on the first row, they're both true. It's the same truth value. But in the middle two rows, there's a true and a false. So they have different truth values. And on the bottom row, they have the same truth value again. So we get another true. So you might want to think of this if and only if biconditional proposition a little bit like an equal sign. So the biconditional is true if they're equal to each other in truth value. Let me do an example, a mathematical example. So, oops. Yeah, let's just go with this. X is less than 2x minus 3 if and only if three is less than x. So here I have just the same inequality rearranged. So I've subtracted x from both sides, and I've added 3 to both sides. And both of these have the same truth value all the time. So no matter what value of x I put in, both of these are the same because they're just rearranged. So this particular example is the kind of place where this statement, if and only if, comes up a lot in mathematics. So like in algebra, when you're solving an equation, each step of your work, you're doing an if and only if. You're saying that they have the same truth value. Okay. And maybe to fill in a blank here. So if I make this one false, if I plug in x equals, I guess 2 would be a good example. That would make this side false. And if I plugged in 2 over here, you would have 2 on the left, and then 4 minus 3. So that's another false. So as long as they have the same truth value, this works. Okay, that's a pretty good stopping point, I think. Are there any questions?
When is 1.3 due?
So I'll be finishing up the section on Monday. That means it'll be due on Friday next
Okay.
week.